Good afternoon. A reminder that this evening is the quiz. I think it's in room 50-340 from 7:30 to 9:30. We are also starting a new topic today. So this lecture and the next lecture will be about operating systems, and you will learn something extremely important about hardware, especially processors, that nothing works without software, right? So this lecture is not really about software. What this lecture is about is that very curious interaction between hardware and software. Both sides have to agree. I mean, hardware won't work unless software makes the right moves, and software cannot function unless hardware tells it exactly what's going on. So this is something that not many people understand deeply, so let's see how far we can go with this. So first, so far what you have seen in 6004, and you may be wondering what is missing, because I can write a program and I can run it, at least on my multi-cycle processor, and you'll be seeing many more things like that. We'll be designing even more sophisticated processors on which you can run programs. So that's not the problem. It's not that we can't run programs. It's just that the reality is slightly more complicated. You know, everything has I/O devices connected to it. Everything has secondary storage connected to it. Every piece of hardware, otherwise it won't be so useful. So until now we could get away with just the ISA abstraction, because that's all you saw between the two. And today what we'll talk about is that there is something more that is needed than ISA abstraction. We need ISA abstraction plus some more assumptions before hardware and software can work together. So basically the point is, this picture you have seen so far is simplistic, and now let's make it more realistic. So the buzzword is operating system in this. So by hardware here I really mean your processor, memory, etc. And at the top level you're running some programs, you know, the applications so-called. But in any real system, what you will find is that there is this intermediate stuff called an operating system. And in fact, even very, very simple devices will have some tiny operating system on it, right, which mediates between hardware and application. We do not give your application direct control over hardware. You know, operating system can always intervene and do things to make your life easier. In some sense. So modern computers cannot function without this resident software, which we just generally refer to as operating system. There are two interfaces in this. It's called application binary interface, which is on the top side between application and OS, and then the supervisor binary interface, which is on the lower side. And if you're wondering why I'm injecting this word binary, it's kind of important the way industry functions, that I should be able to take a binary, run it on this computer, and without any modification I should be able to run that binary on some other computer, assuming it's of the same ilk, you know. So if I have Windows programs running here, I should be able to run them on some other Windows program. And the moment we talk like that, then there are more assumptions involved. There are assumptions involved not just about ISA, because binary by definition is all ISA encodings, right? You're seeing the encoded version of the instruction set. But there are other assumptions involved. How do I call the operating system? And since you're not allowed to look inside this binary, you know, which is being given to you, you just expect it to work, there have to be very, very strong conventions before these things can work properly. So for portability, these interfaces are extremely important. And a bug in interface is a very big deal, and there are lots of holy wars that are fought about these interfaces, exactly what should be included. Should it be an open thing, or should Microsoft control it, or what have you? So just be aware of the fact that there's these things, whenever you come across this word application binary interface, it's a serious issue. Okay, so why we have this operating system? Because we are going to have devices underneath, I/O devices of all sorts. And not only that, the variety of these devices keep increasing, and it's so tremendous that, you know, you all expect that if you buy a printer, it should work, you know, on your system. You should just be able to plug it in and it should work. Well, the reason it works without your application having to worry about it is because you don't talk directly to the printer. You don't talk directly to the disk. You don't say, move your head this way or that way, right? You talk to some other program inside the operating system which abstracts the properties of the device you're trying to call. So your application program doesn't change. All it expects is that there is some device like that. If it doesn't find a device like that, it'll complain. It'll say something missing over here. But once you have it, so operating system essentially is providing you a very useful set of services as well as an abstraction. It's saving you the bother of having to understand the details of every I/O device that is going to be connected to your computer. Without that, I mean, you'll go crazy. Even making a simple thing like a mouse work on your computer, you'll be surprised, you know, how much you will have to write to make that happen. And lastly, but not the least, because of all these things, the notion of multi-programming emerged. That at the same time in your computer, there'll be multiple programs resident. We shift from one program to the next. Why? Often because it takes forever for I/O devices to work. I/O devices work in a completely different time scale than our processors work. Whenever we talk of processors, we talk of microseconds, nanoseconds, etc. When we talk of I/O devices, we talk of milliseconds, right? So in architecture word, millisecond is like forever, right? And if you say 1 second, you say you might as well go home. There is that much time, right? So we very, very different clocks and speeds at which we discuss these things. All right. So if you understand this part, then essentially the reason we are talking about operating systems in this class is because it influences the ISA. ISA requires extension. I have to show you more things that have to be added to the ISA before we can actually support an operating system. And these instructions, of course, will vary from computer to computer, but there is something very generic about them, and for you to be able to understand that exactly, you know, what these instructions do will give you a confidence that when you look up a different computer, when you look up a different operating system, you'll be looking for those things in that. So to get the concepts in this is very important before we get mired down by the details of the specific instructions in this. Now another thing is, now we will start using another name a lot, which we haven't used yet, and that is a process. So far we talk about processor, and we talk of memory, and we talk of programs, and there was no ambiguity what we mean. We have a program and we run it on a processor. But now we have this new thing in the middle called operating system, and we have to introduce another concept so that we have proper vocabulary to talk about it, and this is simply a process. So program, all of you know what it is. It's a bunch of code and data, you know, that is tied to that program. Processor remains the hardware on which you actually execute the program, and the new concept that is being introduced now is a process. Process is an instance of a program running, right? So if I take that program and I map it on my computer, I say, oh, this process is running that program. It immediately raises many interesting questions. So what that means is you could have two different processes running the same program, right? What does that mean? You know, so we'll sort out these things. So the process is an instance of a program execution. Okay, so you have to understand that it includes the processor state, because of course that's the only thing we understand. You know how instructions modify registers. So if you're talking of a process, we have to understand that there has to be a whole processor state associated with it. And as we go further, we'll see a process also has I/O state associated with it. Any device it's talking to in some abstract form, that information is also encapsulated in the processor, in a process definition. All right. Now, having introduced the notion of a process, there is one process which is very important. That's at the center of the universe, and that's called the OS kernel. So there is something which we'll define as we go along, because I can't tell you all the functionalities of OS kernel. So OS kernel itself is a process, right? But it's a very special one. It will have gazillion privileges which no other process has. And any mistake in OS kernel is almost as serious as a mistake in hardware, right? I mean, you'll be very disappointed if your machine didn't add numbers properly. So similarly, the bugs at the kernel level are very serious, very, very serious, and most users will not be able to tell whether the bug came from hardware or software at that point. The point being, it's separate from your application program. Your application program may be fine, and we have to ensure that the supporting stuff is also very good on this. There are three main goals of operating systems, three main tasks operating systems have to, abstractions that operating system has to support. The most important one is protection. Since there are going to be multiple processes inside our system now, in the system we are running, the first and foremost task of operating systems is these processes should not be able to trample on each other, right? I should not be able to write into your space, you should not be able to write into my space, neither of us should be able to write in the process space, because process has its own process, operating system has its own processes running. So protection is by far the most important abstraction that has to be implemented at the lowest level. And you will see the basic idea behind this protection mechanism is address spaces. Your program will have, your process will have an address space, some other processor will have an address space, and these are distinct things. Even though they may use same addresses, you cannot write into each other's space unless we go to some very elaborate sharing mechanism, some protocol, etc. But inadvertently you cannot write in some other processes area. The other thing I already told you is the abstraction. There are gazillion device drivers in your operating system, right? They're not part of the kernel, but they are all there because, somebody has written those programs, and OS is the mediator. OS is the one that says, okay, this application program, when it uses the printer, what, magic words it has to say so that it can actually use the printer. So these services have to be invoked in a very systematic way, and services have to be pretty general, in some sense, so that they have to be written in such a way so that if I change the printer, I was just trying to print, my life doesn't get more complicated. So that level of abstraction is always supported by OS. And the last issue is resource management, and that is again coming on because of multi-programming. So if you're going to have multiple processes running in your system, then somebody has to decide whose turn it is to go next. How much memory should be allocated to a process, right? If there are shared devices, shared files, who has access to these things? All these things are going to be enforced by the operating system. So operating system is a very, very active entity inside your computer. It's always running. Okay, so let's start out with the notion of private address space per process. And you imagine you have a memory in your system. Somewhere OS code is going to reside. Somewhere process 1 program and data is going to reside, somewhere else process 2 program and data are going to reside. And now what conceptually I'm trying to show you is you wrote this program, right? Program 1, program 2. Program 1 is the one that has become process 1, say, for example. The most important thing in this is everybody feels they own the universe, right? So process 1 addresses go from 0 to n. Process 2 addresses also go from 0 to n. And you say, how can that be, right? I mean, how can two things be doing the same address space, right? Because I have already mentioned to you that they're being allocated in different parts of the memory. But in your program, those addresses will look like 0 to n, right, for each process. So there has to be some mapping. There has to be some mapping that goes on in this, that you have a program-generated address. Okay, so this is what is shown at the bottom here, program-generated address, the kind you have been calculating all this time, effective address, etc. And then every time we see that address, we're going to translate it. So this is a very dynamic operation, address translation, and that tells me physically where it is in the system. And you'll be surprised how difficult this is, right, in modern systems, when we really learn about memory systems properly, and that will be the topic of the next lecture, that exactly how does this address translation work? Because if we are not clever about it, our machine is going to slow down dramatically because of this address translation. But we need it in order to create protection. We need to create things so that they have to be, they can reside in separate places. All right, the second thing I said was this notion of scheduling, that since there are multiple processes, what we are going to do is allocate a fraction of CPU time to a given process. All right, and when that time expires, we will switch it and give it to somebody else unless the process terminates, during that time. So a process cannot use more than the time allocated to it, so there has to be some hardware support to enforce this idea. And the picture may look like this, that process 1 runs, and then we invoke the operating system that is shown in a very thin slice over there in some orangish kinds of color, and it decides after that process 2 will run. So process 2 runs for a while, and then again operating system is invoked, and then process 1 runs again, etc. So this kind of scheduling, who's running next and why is this an interesting topic, will also become clear to you as you understand more about operating system. But this is an essential task of every operating system. It does scheduling of processes, and scheduling implies it does resource allocation for every process. The last and not the least is, I keep talking about this abstraction, right? There are all these I/O devices. How does actually I request those services? So these services are requested by something called a system call, which is a very, very general structure. And I'll show you a little later what it means. And system call is going to look like a procedure call, except that it's a call to the operating system. What is the difference? That's what I'll show you in a second, and it will be a very special instruction, to actually say I'm invoking operating system service at this point. And I already listed some of them, like keyboard and mouse and display and file access, etc. They all go through these system calls. Now, this is where ABI becomes very important, application binary interface. For any of these calls to work, there has to be a very strong convention between the operating system and the hardware. All right, so you have to decide, okay, on Windows what will run, right? And Windows is running on x86. So what does x86 support? So we'll talk about that in a second, that operating system and the hardware have to agree. But the most important thing for us right now is, if you are writing an application, the binary interface has specified that you better follow these software conventions if you want to talk to the operating system. And if you don't follow this convention, hell can break loose. You may get very, very strange bugs, if you don't follow the convention, the same way as will happen if you didn't follow the procedure calling convention when you wrote procedures in assembly language programming. And it's going to be exactly like that. So whenever, and we have done an abstraction. So in procedure calls, you're calling procedure such and such. Here you will just say, I'm calling system call 7, right? Or I'm calling system call something. some specific system call. So I will write down the number of that in register A7, and other arguments will be in A0 to A6, etc., etc. So this is really exactly like a procedure call. But it's between you and the operating system to figure out what is the meaning of this call, right? We are only setting up a convention so that you can pass arguments, you get the results back from operating system. But exactly what this call means, operating system will decide, how it's mapped, and it'll publish that. It'll say, oh, if you want to call this service, you have to do the following in your code. Okay, you'll be writing some stuff about this in lab 8. You'll be implementing one specific service. All right, so now let's try to see what is the life cycle of a process, right? So somehow a process is created. So create a process, right? So it's in this state and it's ready to run, it's ready to go. It has everything it wants. And then operating system schedules it. So when it schedules it, then its state changes to executing, right? Now at that time, operating system can decide after a while that I'm going to stop it from running. You say, why bother? You'll see in a minute why. But we may deschedule it, right? So then it goes back to the ready state. Or it could have completed. But very often, another thing can happen, and that is, it can go into a waiting state. It does something, process requests a service, which is going to take a while. And remember, we have already agreed that the service is going to be executed by OS. So what is process doing during that time? Right? So process gets suspended during that time. It goes to sleep. It has been blocked. It's put in the waiting state. And when the condition is finally met, whatever it's waiting for, whenever that happens, then it will be woken up again. Is these high-level ideas clear to everyone? Right? That you create a process, OS will schedule it, it may complete, or it may OS may say, no, you have had enough time and go to something else, or the process may get blocked. It requests a service which is taking a long time, so I may want to do something else during that time. Okay. Now this is the main thing. Once we have this broad idea of what OS does, let's see what ISA extension is needed, what architectural support is needed, and why the conventions are going to be so important. All right, so let's see these IA extensions needed to support an OS. Very first thing in this support is there is a notion of privileged programs. Because if user programs were allowed to do everything, it'll be impossible to implement any kind of protection. Because if every user was omnipotent, then it can go and write in somebody else's space. It's the OS that interferes. They no, you can't do that. So OS has special privileges. It's the most privileged thing. OS kernel is the most privileged process in the system. It'll have more privileges, and the moment we understand that there is a notion of privilege and non-privilege, then its natural consequences that there will be instructions that you can only execute in the privileged mode. If you execute those instructions in the user mode, you'll cause an interrupt. You'll stop. You'll say, sorry, something is wrong. You're breaking some contract here. So lots of things are being said here, that there has to be some way to say what is the mode in which your processor is running. Is it in user, or is it in the user mode, or is it in the supervisor mode? And then take other things from there. You will have privileged instructions. You also have more registers. So until now you have just seen X0 to X31, 32 registers we had. Right? Now we're going to introduce more registers, and the difference between these registers and the registers you have seen so far is, even though they're all 32-bit registers, they have very specific functions. So we think of these registers as how many of these do you have? Well, I can tell you the number, it's irrelevant. We have as many as we need to support our functionality. So you will get a glimpse of what kind of registers, extra registers you have. And remember the saying that if you ever introduce new state, then you will also have to introduce new instructions to manipulate that state. Because state elements, new registers without any instructions to manipulate them, doesn't go anywhere. So anytime you add something, that means there has to be some instructions in the system. And then the mechanism, which I will spend more time on today, is the interrupts. So this is the new concept we are introducing today. And this is the backbone of operating system. That if you understand the overall picture, then you will see these interrupts are the basic mechanism by which we will shift to user program to operating system, back from operating system to user program. And that's a very crucial interaction goes on between hardware and software. And it's going to take some effort to understand, how interrupts work. And that is the main topic of today's lecture. All right. And virtual memory is again, something to abstract the memory and enforce the separation between various users. So interrupts is what I'll talk about today, and virtual memory is what I will talk about in the next lecture. All right. These ISA extensions work only if hardware and software share a common set of, conventions. See, when we talk of add instruction, I didn't have to say that software has to follow some convention. Yes, there is some encoding for the instruction, but beyond that, you give it 2 numbers, it adds it. No longer true. Now the kind of instructions we will give you or we'll describe today, they really have no meaning unless you follow the convention, software convention associated with it. They have a very, very specific goal. Each of these instructions. So it's kind of important to understand this convention. Okay, so what's an exception? What is this mechanism I'm talking about, right? So suppose you have a process and it's executing instructions one by one. Exception, as the name implies, there might be an instruction, which causes an exception, or you deliberately cause an exception to it. And at that point, we will jump to operating system. And we will execute another program, which is called an interrupt handler. So these are the instructions of that. First conceptual difficulty most people have is, I had my program running, right? Something funny happened. I am calling operating system. Operating system doesn't run on a separate piece of hardware. It runs exactly on the same hardware you were using. And that's why you have to understand how this control is transferred to the operating system. And when the service has been provided, how do we jump back to it? And that is what interrupts will do for us, following some conventions that go on with this. Sometimes it doesn't come back to the same instruction. Sometimes it goes back to the next instruction in the sequence. Sometimes it doesn't come back at all. It says, this program is really garbage. I'm going to do something else. All right, but roughly speaking, this is the kind of high-level picture you have. It's called an exception because it's different from the normal flow of the program. Normal flow of the program in this picture is shown to the left, while the interrupt handling instructions are shown to the right. Right-hand side instructions are all happening in the OS. Now, causes for exceptions. The term, and there are many words that are used interchangeably here, exceptions, interrupts. Sometimes people draw a distinction between them, so let me just point out what that distinction is. Exceptions refer to a synchronous event. I executed an instruction and that demanded OS service, right? So it's completely tied to this instruction. That's why it's synchronous. If you execute the program, you come to that instruction, you're going to have an exception and you will execute it. The other possibility is that you were happy but somebody from outside is ringing a doorbell. You say, can I have your attention, please? Right? So they are causing an asynchronous event. Exactly when we look at them, it's really no different than the doorbell at your home. You don't have to pay attention to them, right? Maybe some bad consequences will happen here too if you don't pay attention for a very long time. But I hope everybody understands this very high level distinction. Exceptions are something you are executing a program, you came to this instruction, and then you cannot go further because this instruction is demanding something very, very special to be done. Maybe it was illegal instruction, right? Maybe it caused some protection violation. On the other hand, interrupts are from outside, they're asynchronous events, and they may come and do something, right? They're outside the program. I mean, they may still be inside your computer. Okay, and I cannot remain consistent about my terminology, so I will use the word exception to, by that I mean both, but sometimes I get confused and I may just use the word interrupt. All right, handling exceptions. When an exception happens, the processor stops the current instruction at I, completing all the instructions up to I minus 1, right? Right now this is not a big deal for you because you have only seen very simple machines, right? So you say, what else, right? I have done instruction up to I minus 1, now I'm executing instruction I, right? In modern processors, in high-end processors, you may have 100 instructions from the same program running at the same time. So this idea of a precise interrupt, that if I'm processing something about this particular instruction, you're making a very strong assertion that every instruction before that has completed. Nothing is undefined about that, right? All those instructions have completed. Only then you can process this interrupt. This is called precise. And why is this condition necessary for us? Because if you will recall, the way we define what an instruction does is we work on what state changes it makes. Right? These are the new values of the registers. This is the next value of the PC. This is the next value of the memory. After every instruction, we can ask that question, and there's a unique answer to that. No ambiguity. So similarly, when I say that program has executed up to this point, it defines the state of the system uniquely. Every register, every memory location, PC, everything has a precise value. So that when we start processing interrupts, we know what we can assume about this program, and when we come back from processing the interrupt, we'll have to resume it properly. We'll have to restore that state, the place where the program was, if assuming we want to resume the program. Okay, so the very first thing we do, as that picture kind of implied, if I'm going to go and execute some other program, I have to save this instruction that caused the interrupt. Or if it was an asynchronous interrupt where we decided to take the interrupt, I have to remember this PC because I'll need it to come back here. Not very different from a procedure call, right? When we jump somewhere, we remember where we came from so that we can come back to this point. So that's the idea. This is called exception PC, EPC, all right? And it will be stored in some very special register inside your machine. Not in one of your general purpose registers, but one of these, extra registers we have inside the machine. Now, because we are making a call to operating system, we'll enter the supervisor mode. We'll say, okay, you guys are going to have more privileges, because I'm going from, I'm merely a user, and now I've done something which requires OS services, so I go into privilege mode. and of course, you somehow, when you go there, system has to know why you are here, right? There must have been a reason for the exception. It's called cause, right? There was a cause for the exception. So we will also store the cause somewhere so that the operating system can access it. So it says this program stopped at this instruction, and this was the cause for the interrupt, and it wants this service, etc. All that information somehow has to be passed, and because this exception handler is going to run on the same piece of hardware, what is the very first thing we'll have to do? We'll have to save the state of this program, right? All the registers, PC, etc. We make a copy of them somewhere in the memory. Once we have done that, now instruction handler can run like an ordinary program because it has the whole space available. It can go into whatever it wants. But if you did not save it, then there is a problem, because then you can destroy it, right? You may not be able to come back to where you came from. Exception is transparent to the process. If the exception is due to an illegal operation by the program that cannot be fixed, an illegal memory access, for example, an illegal memory access, the OS aborts the process. Aborting essentially means it just kills it, say, now next guy, whosoever is waiting, I will execute that process. So OS is very, very powerful. You know, it can do all kinds of things. Let me give you two examples of how OS might be dealing with something, because these are very, very different examples. So here is a simple example which every computer has, and that is the notion of scheduling processes. And to enable that, we have this notion that there is going to be a timer interrupt. So first of all, there is a register inside your machine which, you know, just keeps counting. You know, it keeps track of the clock. That's a piece of hardware that is built in, right? And now I can say, actually, you know what, I want to give this process, you know, 50 microseconds to run. So what happens after 50 microseconds? This program is running, somebody else is keeping the clock going in parallel, right? And after 50 microseconds, the ring goes up. Your time is up. Who takes over? OS takes over. It's a timer interrupt. It's external, you know, whenever it happens, you know, whatever instruction you're at, we'll save it, and then we'll say, okay, your turn will come again, we'll save everything about you, restore it again, schedule the next process. So this timer and time-related interrupt is essential for implementing this idea, and this is an illustration of what may happen. You have some kernel running over here, kernel OS, and then it sets timer to 20 milliseconds, and then it schedules process 1. So after 20 seconds, if process 1 didn't terminate, you know, the timer, I mean the OS will take over, and now it will go and execute something. This is the OS code executing at that point for a few seconds, and then it allocates 30 more seconds to process 2. It'll schedule that, and so on. It may resume process 1 after that. Does everybody understand at a high level what's going on here? The reason we can jump around is because we have an independent entity which is keeping track of time, and whenever the alarm rings, the OS says OS interrupt, timer interrupt, which OS processes. Okay. So the other one is very interesting. So I have, say I wrote this instruction, x1 gets x2 multiply x3, and I know that RISC-V had an instruction called multiply. I use it only to discover that I had not implemented it in hardware, because that's also a legal RISC processor, right? I mean, RISC-V comes in many, many varieties. Not everybody has a multiply. What do we do in that case? Well, one way would be that what happens if the code runs, you know, with this multiply instruction, it'll say illegal operation not supported in hardware, right? OS will be invoked, and OS will say bad, 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 you were not supposed to use multiply instruction. But OS could also say, you know what, I can do this multiply even though there is no hardware. I can emulate it in software. I can run a routine, you know, in software to do the multiplication, and I will do that, right? Cause an illegal instruction exception, or I can actually run it. So process 1 causes an interrupt, operating system takes over, and at that point kernel executes the multiply instruction in software. Okay, and you know, we can resume process 1 after that. So we did not abort in this case. When we encountered the multiply instruction, we went from process 1 to OS, which did the multiply. We came back to process 1. Everybody is happy. So why don't we always do it like that? What is the drawback of this solution? I mean, the good thing is now I can run some code, right, on this. Yes?
It's slower because it's running on software.
Exactly. It's slower for 2 reasons. First of all, you're running it in software, right? But you could have yourself written a subroutine and put it there. But this will be even slower than that because you're going to the operating system. And that's where it's running. So really the beauty of this is only that it can transparently do that. You did not even know, your program did not even know that there was no multiply. Operating system provided that service to you, right? In this case. But of course main problem is it will be inefficient if you did it in this manner. Very good. Now if we look at specifically RISC-V instruction handling, exception handling stuff, what all is needed for that. So it has a whole set of registers which are called CSRs, control and status registers. So you will hear the word CSR a lot now. And instead of saying we have 32 CSRs, we will just use them as needed, right? So I think I have listed 4 of them here. So one of them is called MEPC. So prefix M here refers to machine mode or something, it's very low level stuff. So this register always holds the exception PC. In other words, if this instruction causes an exception, hardware immediately will copy the PC of this instruction into this special register. Yes? Right? So you have an exception and I have a special location, special registers where I'll record this. Now, what was the reason for the exception? Was it an illegal opcode? Was it something else, right? Whatever that cause is, there is another register called cause. That's where I will record that. So this will all happen in hardware. If you were implementing these instructions, that's what you will be doing. You'll be saying, oh, what was the cause? And then you will have to write those bits, correct bits, into the cause register. And then, you have a whole bunch of exception handlers, M vector. Where do I go to find the code for running the exception handler? So that is this empty vector given over there, address of the exception handler itself. And the last thing is the status bits. And their status itself is a little bit fuzzy right now in RISC-V. But conceptually something like that is there, where you will record whether it's user level stuff or supervisor level stuff. You're recording some status of the current process. They existed in the earlier versions of RISC-V. They have been taken out in the new version. But for our purposes, it's fine. Let's just assume they're there. Okay. And then you have instructions. So if you have these CSRs, then there is an instruction which will say CSR read, CSR write. Right? So that is what CSR R is and W is. All right? And then there will be a few extra instructions. One of them is mReturn. This is to return from the exception when you come back. There is another instruction which I forgot to write down, which is used for jumping to when you have a systems call, then you will have another kind of instruction that you will use. So a few small number of instructions, which are systems instructions needed to be able to implement this whole infrastructure for supporting operating system. Now comes the most difficult slide in this lecture, and let's see if we can get through it. So I have many devices in my system. I have many different reasons for interrupts and exceptions in my machine. And in fact, when I design my machine, I can't make up my mind exactly how many of these things I want. So the structure that has evolved over the years is very general, right? We are going to provide some basic mechanisms over here, and then you can bind these exception handlers to various codes in your machine. So what I'll attempt to do in the next few minutes is to explain you what this general infrastructure is. This is known as the common handler for all exceptions, right? So this is the very first thing that will happen when you get an exception. What I'm showing you are the steps that common handler goes through. So that's what is shown in orange here, and I'll explain these steps. EH are various exception handlers, so these are just pieces of code sitting there, and then I need some area in the operating system, in memory where I'll be saving things and from where I'll be reading things. So I have shown that area on the top. Okay, so what is the very first thing that happens? It's invoked anytime I see an exception. Hardware will invoke it, all right? Saves registers x1, x31, and the exception PC, etc., in some known place. So that's what is shown here. I will give you more details of this. But first conceptual thing we have to do is the moment exception happens, common handler says everybody has to do this. So common handler is going to do that. It's going to take this, copy all the registers somewhere in the memory. All right? The next thing will be, it will invoke the handler, the service you need. Okay? Now there is a lot of hair involved in this because you have to pass the right arguments to it, right? It will have to set it up so that these things are called. It will look like an ordinary procedure call. To make life more interesting, common handler, etc., will probably be written in assembly language. But most of the handlers themselves, these EH routines are all written in C, because it's very tedious to write assembly language. So how does C also has to agree with our conventions in this? Okay, and then you will go and process this stuff. Everybody got it? We got an exception. We save the exception PC and the state of the processor somewhere in the memory. And depending on what service you needed, we jump to that routine. That routine has access to everything because it will know what is in the memory. And now, whole process, your processor has been cleared out. So it can go and run over there, this code. It runs it, and after that, what does it have to do? When it's done, it may want to come back to the process, and that is what is shown next here, that in order to restore the process, or whichever process you're going to, it will take its state and load the registers one by one in the process. Copy them from the memory into the thing, and CH executes mReturn in this. I forgot to mention, so when we jumped over there, when we invoked the common handler, we already lost our status. We went to privilege mode, right? We were in the user mode, we went to privilege mode. We do all this, now when we are coming back, we have to go back from privilege mode to user mode. So that's also built-in part of the semantics for the return instruction. So at one level, this is going to look very, very similar to procedure calls, but on some other level, there are nuances which you cannot miss, otherwise, you'll make mistakes in this. Is this high-level view of common handler clear to everyone? I mean, is it clear that every exception has to do this? Abstractly, whenever exception happens, save all the state, put it somewhere in the memory, somehow decide what is the exception handler to be run, and at the end of it, you have to come back to the main thing. To do that, you must restore the state, and you must change the mode, from supervisor to user mode again. Okay, so in 1 minute I'll show you this code, because really you have to read this code. Regardless of what I do in the lecture, it will not be enough, but let me just very quickly try to do something. I'm first going to tell you mechanically, then ask you the question why we did it like this. So there is a special register called scratch, and I just store the contents of x1 into that place, wherever that is. So this is the content of x1 that has been stored in this special register called M stretch. And once we have done that, then some operating system has decided this is the area that has been allocated for you to save your state, and that is being pointed to by current processor state. So at that point, you go and load x1 with that value. So you have already saved x1 somewhere, and now you are loading this pointer into the memory, and now I'm ready to copy. So then I go and execute all these instructions, which are going to copy the registers one by one into that area. So I have copied all the registers except for x1. So at the end of it, that's what I have to do. I have to take M, this whatever is sitting in the scratch, and I have to write it back into the memory also. What is still remaining? Where is the exception PC? It is in this register, right? We said there is a special CSR. But you may get more exceptions. So I want to take this exception PC and also store it along with these registers, so that if I have to restore this process, I can do that. So all this state is being stored there, and that is the last bit of code here where you are actually storing the exception PC also as part of that frame. So you have stored all the registers plus exception PC in this place. And then if you see on the next page, essentially it's all about calling the common handler. And to call not the common handler, to call the specific handler for your interrupt. And for that, what you have to do is you have to make sure you pass the arguments. You have to pass in A0 and A1 the right values, right? What are the right values? I'll pass the pointer to where the whole state is, right? And I will pass the next pointer is probably to the EH dispatcher, which code you want to call, right? Which is the exception handler you want to call, and that is the thing, and I don't have enough time to finish this, but even if I read over this code, you will have to study it yourself. So please remember the high-level picture of this. What has to be saved? What has to be restored? Once you remember that, then you will discover there are some nuances here and there. Some register is not available, therefore you have to jump through some hoops, and you'll be able to do it. All right, next time I'll take more questions on this, as well as start with the virtual memory stuff and show you how that is implemented. And good luck with the quiz. It's not difficult, this quiz today. All right, good.